Mechanics, static. The spool. A spool consists of an axle of radius small r and an outside circle of radius big R, which rolls on the ground. A thread is wrapped around the axle and is pulled with tension T and at angle theta with a horizontal, like on the picture. So first question for this problem. Given big R and small r, what should theta be so that the spool doesn't move? Assume that the friction between the spool and the ground is large enough so that the spool doesn't slip. So basically we just need to find the proper point of axis of rotation for this problem, because we know this spool will not rotate if total torque is 0. And such point is only this point of contact. It means that normal force is perpendicular to the ground, force of friction horizontal and going to through the same axis of rotation. It means that this tension must go exactly through this point of contact. In that case, all three forces, friction, normal force and tension, they don't create any torque around this axis, and this spool, for a good enough friction, it will not move. So that's the solution. From geometry we can find that this angle could be found from this triangle. So if this is a small r, this is big R, so we have sine of this angle is sine phi. This is angle phi equal r over big R, and this is the same as cosine for this angle, because together they create angle pi over 2. So it means that cosine theta equal r over r. So this is our solution. Next question. Given big R and small r and the coefficient of friction mu between the spool and the ground, what is the largest value of tension for which the spool remains at rest? So let's write the equation. So first we can write equation for normal force. We have normal force equal mg minus tension multiplied by sine theta. And also we can write condition for which force of friction good enough not to move this construction. So it means that tension multiplied by cosine theta, that's a horizontal force, that must be less or equal to force of friction, which is mu mg minus t sine theta. So that's the maximum possible force of friction. And from here we can find that total tension must be equal or less this expression mu mg over cosine theta minus plus mu sine theta. So this is a maximum possible value for tension. And last question. We see that this angle depends from a small radius. we have to find for which radius. So given r and mu, big R and mu, what should a small r be so that you can make the spool slip from the static position with as a small t as possible. That is, what should small r be so that the upper bound of t is in the second question is as small as possible. What is the resulting value of t? If we look at this expression, we see that the smallest possible tension will be when this bottom part has a maximum. This maximum we can find from find the derivative, but also we can use trigonometry. We have this expression that's equal square root from 1 plus mu square multiplied by 1 over root 1 plus mu square cosine theta plus mu over root 1 plus mu square sine theta. And this is the exactly formula for sine theta plus let's say alpha. Suppose that this is some kind of sine and this is some kind of cosine for some angle. It means that tangent of this angle phi, that's equal 1 over mu. And in that case, whole expression has the same value, root 1 plus mu square multiplied by sine theta plus phi, where tangent phi equal 1 over mu. And the maximum for this expression, of course, equal to when sine equal 1. So that will be total t equal mu mg over root 1 plus mu square. And now look at this expression. We have a sine of this angle this is angle theta, and this is angle opposite to theta. So it means that and let's say tangent for this angle is 1 over mu. So it means that and this is tangent for this angle, and the tangent for this angle is so it means that tangent for this angle is equal to mu, and tangent is this one over small radius. So we have tangent theta equal just square root from r square minus r square over r. This is how to find what is the expression for small r. Because tangent theta equal mu, and that's equal root r square minus small r square over r. From here we can find that a small radius must be equal to expression big R over root 1 plus mu square. So that's the solution.